Hello everyone, and thanks for joining today's webinar. My name is Drew Barbier and I'm a Senior Product Marketing Manager at SiFive. Today's webinar is titled SiFive 2 Series RISC-V Core IP. In the webinar today, we're going to introduce the 2 series products from SiFive, including a look at the architecture and the configurability and feature set of the 2 series. At the end of this presentation, you should have a basic understanding of SiFive's 2 series product and know where to go for more information. This is the second in a 3-part webinar series. In my first webinar, given last week, I introduced the RISC-V architecture. And then next week, I'll be doing a deeper dive and a hands-on into configuring a 2 series core using our SiFive Core Designer tool, as well as using our software development tools to write applications targeting that custom core. The recording from last week's webinar and this webinar can be found in the link below, as well as answers to the questions that were asked during the webinar. We do have panelists standing by to answer questions live during the talk today. In order to raise a question, simply click the Q&A button at the bottom of your Zoom window. At the end of this session, I'll answer a few questions live. Let's start off with an overview of SiFive's core IP products. We partition our cores up into 3 different types of offering. E-cores would be our 32-bit embedded processors. We have public design wins here from companies like Wami, which has our E31 core and a fitness tracker. We also have S-core offerings, which are 64-bit embedded processors. One of our customers here is Fadu, and they're using S5 cores in their SSD controllers. And then we have U-cores, which are 64-bit application processors. The U-cores bring features like RISC-V supervisor mode, which adds support for virtual memory and by extension, high-level operating systems like Linux. Microsemi is using our U5 series cores and their PolarFire SoC products. We also have a few nice quotes as well. I like the one from Fadu, where they say that SiFive's core IP products were 1/3 the area and 1/3 the power of competing solutions. Now, if you look at our entire product map, in addition to breaking down by E, S, and U cores, we also have numbered series on the left. So the 2 series, the 3.5 series, and the 7 series. You can think of the series as defining the base microarchitecture of a design. So the 7 series is our highest performance core series. This is a dual issue in order pipeline. So it's very high performance, but still very efficient. And in the 7 series, we have E, S, and U type cores. Then we have the 3 and 5 series. This is a 5 to 6 stage single issue pipeline. So it's high performance, but still very efficient. It has advanced features like tightly coupled memories, caches on the instruction and data side, and other high performance features. It also offers E, S, and U type cores. And then finally, the topic of today's talk, we also have the 2 series. The 2 series is going to be a power and area optimized implementation, so a efficient 2 to 3 stage single issue pipeline. And inside the 2 series, we have both E2 and S2 products. So again, the E2 being the 32-bit architecture and the S2 being 64-bit architecture. So we'll focus on these cores today. And underneath the series themselves, you'll notice additional cores like the E24 and the E20 and so on. These are what we call standard cores. And so one of the main features of SiFive's product portfolio is the configurability of the product series. So because of this, we often get asked by our customers, what's the performance or what's the area of a given core series? And just due to the number of configuration options, this is a very difficult question to answer. So what we've done here is define what we call standard cores. So standard cores are pre-configured implementations of a core series where we take the core series and select options that we think represent an interesting design point. With the standard core, we take this all the way through a back-end flow. And from that, we can get power, performance, and area benchmarks. And oftentimes, we also realize these devices in silicon. So this is what you see on our development boards. And I'm happy to say we have realized the 2 series in silicon twice now. In addition to just realizing it in silicon, because we've gone through the effort of going all the way through a back-end flow, and the designs are more or less on the shelf, we then turn around and make the standard cores easily available to our customers in the form of FPGA evaluations and RTL evaluations, which are available from the website. So the 2 series itself is very configurable and scalable from area-constrained devices. So I'll talk about the sort of minimum configuration of the 2 series, which can be as small as 13,500 gates. And then as far as the standard cores go, we have balanced implementations in the E20, which is about 90 to 95% the performance of a Cortex-M3, though in about 60% of the area. And then we have high performance implementations like the E21, which is higher performance than a Cortex-M4, though in less area. And then completely unique offerings such as the S2 and the 64-bit S21. And these are sort of the smallest 64-bit CPU offering in our portfolio, and really give ease of integration into larger SoC systems. And I'll talk about all of these over the course of the webinar. And really everything in between, because the processors are so configurable and we make it easy to do so. This gives our customers the ability to configure a processor to exactly meet their requirements for different features or performance levels and so on. And I'm happy to say, since we launched the 2 series in June of last year, we have over 25 design wins now. And I think this number is a little bit out of date as we're approaching 30. So I mentioned configurability, so I'll talk about the configuration options in this webinar, but in next week's webinar, we'll specifically go into configuring a 2 series core using the SiFive Core Designer tool. And the SiFive Core Designer tool is a web-based configuration tool. And this is interesting because it makes it very easy to configure the design. And because it's web-based, that means there's no on-site tools to install. There's no licensing servers that have to be spun up. There's no tickle scripts that have to be used to configure IP or anything like that. Everything is done through the Web Designer tool, Core Designer tool. And after customers configure that their core in SiFive Core Designer, the RTL is then made available in their workspace where it's easy to download and get started. So again, in next week's webinar, we'll go through a lot more detail in this specific process. Now let's take an overview of the E2 series features themselves. So I mentioned the E2 series is our most efficient and smallest series in the SiFive RISC-V IP portfolio. And it has a configurable, it implements a number of the RISC-V standard extensions. So it implements the RB32E, I, M, A, F, and C ISA extensions. And again, most of these are optional. For example, you can choose between the RB32E or I instruction set if you want to optimize for area. Multiplication is also an optional extension, and the same for floating point and atomics. And I'll go into more detail on each one of these later on. The core itself implements a 2 to 3 stage optional Harvard pipeline, and I'll talk about that as well on the next slide. It has efficient memory access and really the ability to customize the memory subsystem. So all the ports that you'll see are configurable. The addresses and sizes of the ports are configurable, so the memory map itself is completely user definable. We also have optional tightly integrated memory, which provides direct access to SRAMs without having to go across the bus. The E2 series is also the first RISC-V core that adds support for the core local interrupt controller. This is a new sort of fast interrupt controller standard that has been put forward in the RISC-V Foundation. And what it provides is hardware interrupt prioritization and nesting. It also offers very efficient and low latency access to interrupt service routines. so much so that it only takes 6 cycles to execute the first instruction of an interrupt with the 2 series pipeline and the CLink. And finally, the E2 series also implements the SiFive custom instruction extension, which allow customers to easily add support for custom instructions. And we'll talk about all of these over the course of the webinar. The S2 series extends the 2 series to 64-bit, so it takes all the features of the E2 and bring it to the S2 series with 64-bit capabilities. So what the 64-bit capabilities bring are specifically higher performance arithmetic operations, for 64-bit arithmetic. It also doubles the load and store bandwidth as well, because load and stores are now 64-bit. And I think more critically, it makes it easier to integrate the 2 series into larger SoCs. And the reason for this is because the S2 series, because it's a 64-bit, it can directly address greater than a 32-bit physical address space. So if you're putting controllers into larger 64-bit SoCs, the S2 can directly address the entire memory space. And just because it's 64-bit doesn't mean that it has reduced code density thanks to the RISC-V architecture. I talked about this last week as well. But the 64-bit architecture also supports the compressed extension, which brings with it 16-bit instructions. So even though it's a 64-bit, native 64-bit architecture, the instructions still are encoded in a 16-bit opcode space. And really, there's no competitive equivalents on the market today to the S2 series. So let's take a little deeper dive into the 2 series memory subsystem. So I mentioned earlier that it's an optional hardware interface, and what we meant by this specifically is that you can configure the 2 series to have 1 or 2 native interfaces from the core. And what this means is with a single interface, it is a smaller area, but over this one single interface, all instruction and data operations pass through. But you have the ability to add a second core interface to the 2 series cores. And with the 2 core interfaces, this gives instructions and data separate interfaces to the outside world. So with the 2 interfaces, it adds additional area, but with that area comes additional performance as well. And we'll look at benchmarks in a few slides. We also have a number of configurable ports in the 2 series. So we'll start off with the system ports. So we can configure the 2 series with 1 or 2 system ports. And the system ports would be used to access main memory in a system. And these ports are configurable in their base addresses and their size of the address space that each one would address. We can also configure the protocol that the system ports use. So we can support CLink interfaces as well as AMBA AHB and AMBA AXI interfaces. And we can also support different data widths on these protocols for helping integration into different designs. In addition to the system ports, we also have optionally 2 low latency TIM banks, and what TIM stands for is tightly integrated memory. And these TIM banks can be used to store instruction and data in a manner that's tightly coupled to the core with guaranteed access times. So the TIM banks don't have any strict enforcement of what type of data they have, so they can, both banks can store instructions and data, and both banks can be accessed by either port on the 2 series core. So if you only have a single port, then that single port can access both TIM banks, or if you have separate instruction and data ports out of the core, both of those ports can access either of the TIM banks. So there's no restrictions really on what can be placed in which memory or which type of access that can access the bank. In addition to the TIMs, we also have an optional peripheral port. The peripheral port is interesting because it supports RISC-V atomic instructions. And so I talked about atomic instructions in the previous webinar, but these allow for single instruction read, modify, write operations. And so the peripheral port has special logic to guarantee atomic access for those type of operations. And then finally, we have an optional front port on the design. The front port is a master interface into what we call the core complex. This allows other masters in your system to directly access the memories in the TIMs, or to have writes pass through to the system or peripheral ports. So again, everything in this diagram that's marked with dotted lines or dotted arrows, these are all optional and configurable parameters in the design. So let's take a look at the sort of minimal configuration of the 2 series. And this is kind of a design point we call the E2M. So we reached the minimal design point by implementing the RB32EC architecture. And so the RB32E options aren't available today on the website, but they will be in sort of the next release. And I'll talk a little bit more about RB32E in another slide here. But the minimum configuration would use the embedded extension, which reduces the number of integer registers from 32 to 16. And as you can imagine, this has the impact of reducing the area of the design. We also use the area optimized interrupt controller, which still has support for up to 16 peripheral interrupts in this specific configuration. And then we have a single 32-bit tile-like interface for addressing instructions and data with the rest of the design. So, you know, there's not much here, but that's the point of this configuration. It's very small. And because of that, we're able to realize an extremely small implementation that only consumes 13,500 gates, or 0.005 square millimeters in a 28 nanometer design. Now with this, I do want to point out that we're not necessarily sacrificing performance here, because if we look at the performance of this particular core, we're only implementing 1.07. If you look at the performance of Drystone on this particular core, we still reach a performance level of 1.07 DMIPS per megahertz, which is quite high performance for this type of design. Also take a look at the S21 standard core. So the S2 series was launched in April, so a few months ago, and we'll be launching the S21 standard core on the website soon. So the S21 looks and feels just like the E21 standard core, with the exceptions that it's obviously 64-bit, but also implements 64-bit AXI interfaces on the ports. And if we compare the S21 to our S51, which is sort of the next level up in the 64-bit embedded profile, we see that the S21 is about half the area of the S51. So this is a very small 64-bit processor. But having said that, just because it's small doesn't necessarily mean it's not performant. So we do still reach sort of 1.6 DMIPS per megahertz, as well as 3.2 core marks per megahertz. I'm not going to cover the other standard cores in detail in this webinar. All of the information is on the website, and we will be refreshing that information soon. And some of that information that will be refreshed is the recent performance improvements that we've made to the designs. So the February release of the 2 series saw improvements to the hardware multiply and divide units that led to increased benchmark scores. And so we'll take a look at some of these benchmarks compared to their ARM equivalents. So first off, I'll note that the E2 min config, we mentioned Drystone being 1.07 DMIPS per megahertz. If you compare that to the DMIPS per megahertz of the Cortex-M0 Plus, and again, these are all using GCC, so equivalent releases of GCC with similar compiler flags. The E2 min config is higher performance than the Cortex-M0 Plus in Drystone. And then if you look at some of the other comparisons, E20 versus Cortex-M0 Plus is significantly higher in performance in both Drystone and CoreMark, so much so that the E20 is almost on performance parity with the Cortex-M3. And then if you look at performance benchmarks of the 21 and 24 against the M3 and M4, you'll see these are quite a bit higher performance as well. And then the S21 being higher performance still. I'm not going to go through this chart, but this is to, further show the comparison points between sort of the SiFive standard cores and the ARM equivalents. But I want to point out the column here on the left, where we have the configurability of the E2 series in general. So with the single core series, we're able to address sort of almost the entire ARM Cortex-M configuration space. So we do have point configurations in the standard core, but really the strength of the SiFive offering is in the configurability of the series. And this really allows our customers to tailor the SiFive cores to their specific requirements, be it for specific performance points, or area points, or power consumption points. So now we'll move into more detailed discussions on the 2 series features. And we'll start off with the RB32E. So this is a feature that will be released in the next release of the 2 series. And I mentioned earlier that the RB32E extension reduces the integer register file from 32 registers to 16. This has an impact on performance, which can be as significant as a 25% area reduction, depending on the core configuration. And we say that because, if you configure the core to have floating point and all these other features, then reducing the register file will have a slightly smaller impact on the overall area reduction. But in this sort of E2 min configuration, for example, just moving from RB32E I to RB32E results in a 25% reduction in area. But at the same time, the impact on performance when moving from the I instruction set to the E instruction set is quite minimal, and it's usually quite a good trade-off to make. So if you look at Drystone specifically, we only see about a 6% impact on performance when moving from RB32I to E. So I think the RB32E option in the 2 series will be quite a popular option from our customers. Now, having said that, just because you use the RB32E option, that doesn't prevent you from using the other extensions as well. And so you're perfectly free to mix the RB32E option along with the multiplication extension, the atomics extension, floating point, and so on. And of course, obviously the RB32E option is going to be fully supported in SiFive tools and software. So it's already supported in the toolchain distribution that we have on the website today, which was released in February. It also adds support for, we also have support for this in the latest branches of Freedom ESDK and Freedom Metal. And, from a customer application standpoint, there's really no changes they have to make to their code at all. If you're writing code in C, then really this is just a compiler command line change, and that's it. The compiler will take care of the rest and implement the RB32E ABI. The 2 series also has optional M and F extensions. So the M extension, in addition to being optional, we also have several different performance levels of the multiplier itself to choose from. So the highest performance one would be the pipeline multiplier. This is a sort of a 2-stage multiplier, but because it's pipeline, it allows for back-to-back multiplies to retire in consecutive cycles. So you really still get that high performance, really single cycle multiply performance, but it's still efficient from an implementation standpoint in terms of area and max frequency. In addition to the pipeline multiplier option, we also have 4 and 8 cycle multiplier options, and these are really interesting for area sensitive applications where they still have a considerable number of multiplies that are in their code. And then we also have the option to remove the hardware multiplier entirely from the design. And this is what we've done in sort of that E2M configuration. And, this is interesting for extremely area constrained implementations or implementations where they just don't have multiplication requirements in the source code. You know, popular applications here might be where it's just a control code processor, where it's just comparing values or data and branching and things like that. Now we'll note that when you add the M extension to the 2 series, this does also include an area efficient hardware divide. So this gets you a 1 bit per cycle hardware divide with an early out. So this is interesting because it sort of differentiates itself from other sort of smaller designs like a Cortex M0 or M0 Plus, which don't have hardware divide. We also have optional single precision floating point. So this is a fully IEEE 754-2008 compliant floating point unit. And it has a number of features that are interesting to it, like fuse, multiply, add, iterative divide and square root, float to integer converters, and full subnormal support. So the floating point unit is interesting for a number of use cases. And I do want to call out that a double precision floating point unit is on the roadmap for the 2 series. Now, if you take a look at the Interop controller, we have 2 controllers that you can choose from, sort of an area optimized controller in the CLink. This is a controller that allows for up to 16 or 48 peripheral interrupts, depending on whether or not you have the E2, which is 32-bit, or the S2, which is 64-bit. And this interrupt controller is perfectly capable for applications which still require interrupts, but maybe light management of the interrupts. And what I mean by that specifically is the priority scheme of the interrupts are fixed, and I'll talk a little bit more about that in the next slide. But the CLink does still have support for limited vectoring capability. And again, I'll talk about the CLink a little bit more in the next slide. However, we do also have a more feature-optimized interrupt controller that we call the CLink. The CLink interrupts the fast interrupt controller standard, which is being put forward in the RISC-V Foundation. And it's a more featureful controller which supports up to 1,008 peripheral interrupts. And it has hardware prioritization of the entire, of all the interrupts connected to it, as well as nesting and vectoring in hardware. In addition to that, it is also configurable with a configurable number of priority bits, and these control the number of interrupt nesting levels, for example, and allows customers to tune the area of the interrupt to meet their sort of application performance level requirements and area requirements. So taking a little bit closer look at the CLink controller, again, specifically you would use the CLink when you're optimizing for area over interrupt latency and prioritization, dynamic prioritization. And the reason for that is the CLink has a simple fixed priority scheme where the higher the interrupt ID, the higher the priority. The CLink does, however, still have a optional vectoring mode. And when the CLink is in the vectoring mode, then you can populate a vector table with jump instructions to specific C code handlers. And what this does is help reduce the interrupts latency, in that you don't have to have specific hardware to then go and read registers before branching to specific interrupt service routines. The hardware will automatically branch to the appropriate routine based on the interrupt ID. Now, because the vector table is based on the interrupt ID, the highest ID is the highest priority interrupt, and it occupies the top of the vector table. And this is a little bit of a special place in the vector table, because what that means is there's no interrupt vectors above it. And this allows you to start implementing your interrupt service routine directly without having a jump to another handler. So it saves you a branch in the latency for handling the interrupt. Now, if we take a look at the core local interrupt controller, or CLink, this is really more of a simplified interrupt scheme, which allows for very low latency interrupt servicing, including hardware prioritization and preemption. So I mentioned earlier, it supports up to 1,008 peripheral interrupts. And this is in addition to the architecturally defined timer and software and external interrupts. Now, having said that, the CLink does drive interrupts to a single core in the design, but the CLink still has the machine external interrupt, which allows for SiFive customers to connect a PLIC in a larger multi-core design to the CLink. And this still enables the multi-core interrupt distribution in the same architecture that's in the rest of the RISC-V ecosystem. So in other words, the CLink, in this case, sort of subsumes the standard CLink functionality, as well as adding these additional capabilities to interrupt prioritization and nesting to a specific core. Now, one thing about the CLink that makes it interesting is, or the 2 series interrupt handling in general really, is that it's only 6 cycles into the first, to fully execute the first instruction of an interrupt service routine. And we have specific examples in a blog where I outline that an entire interrupt service routine can be serviced in only 18 cycles of the core in the 2 series. So very low latency interrupt handling and high interrupt throughput. And in this case, I mentioned the way the vectoring occurs in the CLink, but with the CLink, the vector table functions a little bit differently in that it contains addresses to the C handlers for a given interrupt. And this is a little bit different than the CLink, which was a jump instruction to the handler. So in this case, the hardware actually reads the address of the handler in the vector table and branches to the actual interrupt vector automatically for you. Now, the CLink can have up to 256 levels of nesting, and within the levels, you can have programmable priorities as well. And then the CLink also has an easy-to-use programmer's model, and I have a slide on this in the next slide. But there's GCC function attributes that you can use entirely, so that your entire ISR and application can be written in C code and not have to go down to the assembly level. The CLink also has additional software interrupts, which you can use to for sort of low priority pending interrupts, if you will. So you can use the software interrupt and programmable priority levels as software needs. And then, of course, in the SiFive software deliverables, we have drivers and interrupt service routines and things like that already written for you. So if we take a look at this, what it actually looks like in C code for CLink interrupts, if you followed my webinar last week, this looks pretty similar, but the difference here is that the function has a slightly different attribute. In this case, we're calling out the SiFive CLink preemptible attribute, and this would be the actual C code handler of your interrupt service routine. So to set this up entirely, we now have a vector table in software where we're loading the address of the ISR. So in this case, this machine timer interrupt handler, we're loading the address of this function into the vector table. And then in the code, we have a new CSR, which has a pointer to the vector table. So in this case, this is just a pointer to the vec table array here. And in this regard, the vector table is sort of relocatable. So you can swap vector tables if that makes sense for your application, where you have different vector tables for different parts of your application. So other than that, it's almost exactly the same as normal RISC-V interrupts. You would set this up by first writing mtvec and setting the mode in mtvec to the CLink vector mode. And from this point on, everything is set up. The entire interrupt handling is done in your C code, and there's no need to drop down to assembly code. And I put this diagram up to compare with the diagram that I showed in my webinar last week. So the difference here being each core would have its own CLink controller in a multi-core system, and you could potentially still have a CLink which could distribute sort of more platform level global interrupts to each core or heart in the system. but the cores themselves can also have local interrupts which are routed directly to the cores themselves, as opposed to going through the platform level interrupt controller. And oftentimes we see this in sort of heterogeneous architectures where customers are implementing different mixes of S cores and U cores in the same design, and they may want to route specific interrupts to the S cores that are maybe secure interrupts or specific to the S core, not necessarily part of the application class processor as well. You know, maybe this is part of a power management subsystem and things like that. So we have the ability to partition some of these interrupts and capabilities of the core in the larger SoC using these local interrupts. The 2 series also implements physical memory protection, which I talked about last week as well. So I won't spend too much time on it, but the 2 series core can be configured with up to 16 PMP regions, and the regions themselves can protect areas in memory as small as 4 bytes. So the 2 series also supports region locking, and again, region locking, in the normal case, the PMP enforces permissions, access permissions on user mode accesses to memory locations in a region. But whenever you lock a region, the 2 series then enforces access permissions on all accesses to that region, be it from machine mode or user mode. So in this way, you can lock a potential region from being accessed indefinitely from software executing, even in the most privileged state on the 2 series core. And the only way to unlock a region is to actually reset the core. We're also adding an optional micro instruction cache to the 2 series, so this will also be in the next release of the design. So the 2 series micro instruction cache enables fast and efficient accesses to maybe slow memories in a design, or maybe this is external SPI flash, for example, or maybe it's just memory that's far away from the core itself. So the instruction cache itself is configurable in the cache line and the cache size. So we allow you to pick from 1 to 16K cache size, and the line size as well is configurable from a 32-byte line to a 64-byte line. The micro instruction cache itself also has a software-defined cacheable region, and you'll program these regions using the same encoding as the PMP, so that it uses sort of this naturally aligned power of 2 encoding, and that allows you to define regions in the address space that are sort of cacheable by this instruction cache or not. The 2 series also supports ECC options as well on the TIM memories. So the ECC itself supports single error correct, double error detect, and this would be on the TIMs in the 2 series. Now, in addition to the ECC, we have what's called a Bus Error Unit, and so reporting of ECC errors are fed into the Bus Error Unit, and the Bus Error Unit can be used to can be programmed to notify the CPU of these errors. So in that way, it can generate interrupts so that software can track the number of ECC errors that are occurring and from which cores. It also has signals that can go to external to the core complex, and these signals can be used to connect it to sort of more system level error management controllers that can track numbers and types of errors that are happening in a system in general. And then on double bit errors specifically, there is a halt from tile signal that gets raised, signaling that there was a double bit error, which is unrecoverable. Our cores also have what's called the SiFive Custom Instruction Extension. This is a predefined interface that exposes opcodes in the RISC-V custom opcode space over this interface and allows customers to add their own functional units for handling these custom instructions. In this interface, we expose 2 source registers, which can be used as sort of function arguments to your custom logic, and then a single destination register, which can be used to pass the results of those operations back to the SiFive processor. So this the SkyPort, or SiFive Custom Instruction Extension, is tightly coupled to the core, so all pipeline hazards are handled on the SiFive side. So if things like interrupts or exceptions happen, that's all taken care of for you by the SiFive implementation. Now what this gives you is a very easy to use interface that allows you to implement custom instructions using your own design in a manner that's sort of typical of a normal design flow. You know, these interfaces are exposed in Verilog. You would use Verilog to implement your own functional units using your standard EDA design flow. So there's no custom programming languages or anything like that to learn here. Now the Sky interface supports custom instructions which can consume 1 or 2 cycles. We also have an interesting capability called SiFive Insight. SiFive Insight was created specifically to help customers debug their designs in simulation. And so what it is specifically is we've had the architects of all of our core series curate a list of signals into a single Verilog module that we call it the Insight. And in this module, we have very clear and intuitive signal names with a logical hierarchy that allow customers to debug simulation waveforms very easily. And so again, these signal names are picked by the architects and documented clearly in the design. So we also have machine readable versions of these signals as well. So if you wanted to consume these signals with other EDA tools, that capability is there as well. And I'll talk about SiFive Insight on the next week's webinar, where I go a little bit more hands-on with the deliverables. The 2 series also supports compact JTAG for debug. So in addition to standard JTAG debug, for pin-constrained devices, we support the IEEE 1149.7 standard, which defines a 2-wire JTAG interface. And this is fully supported with our developer environment, whether or not you're using Freedom Studio with Holomex probes, or if you're using third-party probes like Sega JLink. So speaking of debug, let's talk a little bit about software development as well. So there's quite a bit of activity in the embedded ecosystem today, and really is maturing quite rapidly. So SiFive have our own tools, and I'll talk a little bit more about that in the next few slides, so I won't spend much time on it here. But we are supported commercially for some time now by some very popular third-party tools. Sega, for example, have support for SiFive devices in their probes as well as in their Embedded Studio IDE. The likes of Lauterbach also have support for SiFive devices, and both Sega and Lauterbach have had support for SiFive for over a year now. So these tools really are quite stable and mature. Also, IAR joined the RISC-V Foundation last year, or in the process of developing their RISC-V offering. And Ashling is another commercial software offering, tool offering as well. In addition to that, there are a number of different commercial and open source operating systems that support the 2 series. You know, we have a few listed here, but for example, we have really good support and are quite active in the Zephyr Foundation. We're also active with FreeRTOS as well, so FreeRTOS has official RISC-V support today. There are also offerings from commercial RTOS providers like Express Logic and so on and so forth. So if you take a look specifically at SiFive's embedded tool offering, you know, really at the top, the top level interface for this is going to be Freedom Studio. Freedom Studio is an Eclipse-based IDE for developing and debugging SiFive applications. And so this Freedom Studio really wraps together a number of open source technologies that we use at SiFive. The first being the toolchain. So included with Freedom Studio is a binary distribution of our toolchain. And both Freedom Studio and our toolchain support all three operating systems, so be it Mac OS or Linux or Windows. And Freedom Studio now builds on top of Freedom ESDK and really acts as sort of a front end to the Freedom ESDK. But Freedom SDK is also standalone as well. So if you're more less of a Eclipse or GUI software developer and you're more familiar with sort of makefiles and command line driven development, Freedom SDK is there as well on our GitHub. And this provides sort of command line driven workflows and examples and utilities, including sort of pre-built BSPs for all of our standard cores and development boards. And so inside Freedom ESDK, we have a number of examples and benchmarks that are growing all the time, as well as sort of scripts and utilities to help use Freedom ESDK to target our different platforms, be it the FPGA developer kits or the RTL test bench that we deliver with our IP. And then Freedom ESDK itself builds on something that we call Freedom Metal. And you'll start to hear more about Freedom Metal from SiFive going forward. So this Freedom Metal is a library that's used to create really portable bare metal software. And the idea here is that it's a library that if your software targets this library, then we are guaranteeing that it's portable across our entire product portfolio. And so Freedom Metal itself defines the API, but as part of it, it has BSP generation tools and utilities as well. And so today, with the configurability of our cores, it changes the software developer environment and the BSPs. And so today, we have application notes and scripts and helper utilities to help generate Freedom Metal compliant BSPs for custom cores that are coming out of our SiFive Core Designer tool. And going forward, we'll actually include these custom BSPs directly in the deliverables themselves. So as you can see, our software story sort of builds upon itself from the base level Freedom Metal, bare metal libraries, all the way up to sort of the higher level Freedom ESDK, where we have these high level examples and applications and benchmarks and so on. And then Freedom Studio at the top, which gives you that nice GUI for driving either Freedom ESDK or GUI graphical debug and so on. And all of this is available on our GitHub website. So if you go to github.com/SiFive, you'll see access to Freedom ESDK, Freedom Metal. We also have a Freedom Tools repository, which contains the source code and build scripts for our binary toolchain distributions. And again, just a snapshot of Freedom Studio. There's not much to see here, and I'll be going over Freedom Studio in a little bit more detail in next week's webinar. But if you're familiar with Eclipse-based software developer environments, you'll be at home with Freedom Studio. And so that concludes today's webinar. For more resources, I would recommend you go to a couple different places. So first off, RISC-V.org. This website has links to the RISC-V specifications, also ways to sign up for the RISC-V mailing list, and the workshop proceedings as well. The workshop proceedings are a great resource to come up to speed quickly on RISC-V and to see what's happening in the ecosystem at large with presenters from a number of different companies and markets. GitHub is also a great utility, a great resource rather. So a lot of what SiFive does is open source and developed publicly on our GitHub page. Same thing for RISC-V itself, so it has its own GitHub repository at github.com/RISC-V. And then finally, SiFive.com, so our main web page, Here you can find links to more information on our IP, as well as how to purchase and get started with our development boards, our tools, our user forums, and SiFive Core Designer tool as well, which I mentioned here several times. So this is a three-part webinar series I mentioned earlier. So the recordings for the webinar series are going to be on the URL on the bottom of this page. So last week's will be, it's posted already actually, and the proceedings from this webinar will be posted there shortly. And then finally next week on May 23rd, we'll do a more hands-on webinar where we actually use SiFive Core Designer to customize a 2-series core, and then use Freedom ESDK and Freedom Studio to write targeted software for this custom core. But if you're interested, I don't want you to wait till next week to see me go through the hands-on approach. I would encourage everybody to go to our website today and sign up for the SiFive Core Designer beta. So with SiFive Core Designer, you can go onto the tool today and customize see the customization options that are there today. I mentioned a few features on today's webinar that are sort of coming over the next release. And so, look for updates here and blogs outlining the next release of the 2 series and SiFive Core Designer and our IP in general coming soon. So no need to wait for next week's webinar. Feel free to join, sign up for a SiFive Core Designer account today and play around at your own speed. Okay, so with that, I'll turn to some of the questions that were asked here. But if you have any questions, feel free to paste them into the question and answer box at the bottom of the Zoom window, and we'll do our best to answer them live. So one question that we got is, what debug interfaces and tools are available for parts for the E-cores? So I think I covered this over the course of the webinar, but SiFive have our own debug tools in Freedom Studio. There's also sort of industry standard debug tools as well with Seger and IER and Lauterbach, and those guys having support for SiFive devices now. Interfaces specifically, so we have JTAG interfaces and compact JTAG as well if you need a 2-pin debug interface. Another question was, does Freedom Studio work with Freedom U? And the answer there is yes. So Freedom Studio itself supports debug generically of RISC-V. So you can use Freedom Studio to graphically debug Freedom U cores like the FU540 that's on our Hi5 Unleashed device. All right, so if there's no further questions, thank you for joining today's webinar. And if you want to join next week's webinar, please go to the URL linked here and register to sign up. Again, this will be a more hands-on webinar. And until then, we'll post the recording of this webinar as well as full transcripts of the questions and answers shortly. Thank you very much.